In this video, I want to talk about linear independence in Rn. We're going to talk about this using an example as a guide, and we're going to use that example to kind of develop some ideas about linear independence. So we're going to determine whether the set 2, -1, 0, 1, 1, 0, -1, 2, 0, 3, 1, 2, -1, 1, 2, 1 is a linearly dependent or independent set in R4. So notice we have 4 components in each of these vectors. That's how we know we're in R4. Whenever we have a set of vectors, or really a set of elements in any vector space, and we want to determine whether or not those vectors are linearly dependent or independent, we always start by considering a linear combination of those vectors and set that equal to whatever the 0 vector is in that space. So we start by considering the following equation. So some constant times the first vector, 2, -1, 0, 1, plus another constant times the next vector, 1, 0, -1, 2, plus another constant times 0, 3, 1, 2, plus a fourth constant times -1, 1, 2, 1. And we set that equal to the 0 vector in whatever vector space we're in. Right now we're in R4, so the 0 vector looks like a 1/4 vector of zeros. And we ask ourselves, what can happen? So what can happen in this scenario? In other words, we want to know, what are these constants? What are they allowed to be so that this system, that this linear combination of vectors is equal to the 0 vector? We basically have 2 options here. So let me get a different color. So option 1, the first option is that the only values of C1, C2, C3, and C4 that satisfy the equation are when they all equal 0. So is when C1 equals C2 equals C3 equals C4 equals 0. That's one option. If this happens, then the vectors are linearly independent. Then the vectors are linearly independent. Meaning I cannot write any of these vectors as a linear combination of the others. If I could, then there would be non-zero scalars that would allow me to combine these in a way that I would get the 0 vector. Okay. The other option, or option 2 here, the second thing that can happen is that there are some non-zero values for these constants. There are some non-zero values for the constants, values for C1, C2, C3, C4 that satisfy the equation. Now, if this happens, then the vectors are linearly dependent. Vectors are linearly dependent, meaning I could find, non-zero constants. Say I could find like a 2 and a -1 and a 3, and I could write some of these vectors as linear combinations of the others. So to recap, if either the only values of C1, C2, C3, and C4 are 0, that would mean we have a linearly independent set, or at least there are at least some values that are non-zero, then we'd have a linearly dependent set. So let's go ahead and look at how we can determine this. Now, this linear combination of vectors that I've written down here is actually giving me a system of 4 equations. So where are those 4 equations coming from? Well, it's exactly because I have 4 components in each vector. So the first components, or the first elements of each vector, is giving me one equation that tells me that 2c1 plus c2 plus 0 times c3, so I just won't write that, minus c4 equals 0. The next elements are telling me that negative 1c1 plus 0c2 plus 3c3 plus 1 times c4 equals 0. So that's giving me negative c1 plus 3c3 plus c4 equals 0. Actually, let me write that first equation a little better there. Okay, and then I have my third elements of, or my third components of each vector, giving me a third equation. Negative c2 plus c3 plus 2c4 equals 0. And finally, I have my fourth elements, or my fourth components of each vector, telling me that c1 plus 2c2 plus 2c3 plus c4 equal 0. So I have 4 equations, and my unknowns are the constants c1, c2, c3, c4. So if I wanted to solve this system, because remember we want to find out what's happening with these constants. Are they all 0, or can some of them be non-zero? So I go ahead and I write down my augmented matrix for this system. Augmented matrix. And I would get the matrix 2, 1, 0, negative 1, 0, my right-hand side, negative 1, 0, 3, 1, 0, 0, negative 1, 1, 2, 0, and then my last row, 1, 2, 2, 1, 0. And this is an augmented matrix, so I'll go ahead and draw a little line there to remind us that we have an equal sign. It's a system of equations. And if I were to do reduced echelon form, let's just remind ourselves that each of these columns is corresponding to one of the constants. So the first column are the coefficients on C1, the second column are the coefficients on C2, coefficients on C3, coefficients on C4, and the last column is our 0 vector, the right-hand side. So if I were to do reduced row echelon form, or row operations to obtain a reduced row echelon form, I would get the matrix 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 0, 1, 0. Okay. This tells me that 1 times C1 equals 0. C1 equals 0. Second row is telling me that C2 equals 0. Oh, sorry, this should be a 0 here. C3 equals 0, and C4 equals 0 as well. So the only solution, to this system is that all of the constants have to be 0. So the set of vectors is linearly independent in R4. I'll go ahead and put a box around that. All right, so we have our set is linearly independent, but I want to also bring this back to some things we know about matrices. So I'm going to scroll over here. I just have rewritten Sorry, I want to make sure this doesn't move anywhere. All right. So I just rewrote the vectors up here beforehand. This was our original system, and we had this augmented matrix. And we wrote down this augmented matrix because, again, we were trying to figure out what's happening with those constants in the linear combination of these vectors when I set that equal to the 0 vector. Now I can rewrite this system, this augmented matrix, as a matrix equation where I've got, actually let me use a different color here, where I've got my coefficient matrix, 2, 1, 0, -1, -1, 0, 3, 1, 0, -1, 1, 2, 1, 2, 2, 1, times a column vector full of the constants C1, C2, C3, C4, and I'm setting that equal to a column of zeros. So I've just rewritten this system here. Instead of the augmented matrix, I've just got the coefficient matrix here. If I multiply that by a column of my unknowns, I would recover the left-hand side of this system. And I'm setting that equal to my right-hand side, which is all zeros. Now I want to point something out here, that the first column of this matrix is actually the first vector in our set. The second column of our matrix is the second vector in our set. And so on and so forth. So the third column is the third vector, and the fourth column is the fourth vector. And that's always going to happen, because when we wrote down this system of equations, all of the things that are multiplying C1 are going to end up in the first column. That happens to be V1. The vector V1, if I call this V1 here, my first vector in my set, V1 is the vector that's multiplying the constant C1, so it's ending up in the first column. Same thing for V2, that's all of the elements being multiplied by C2. There's V3 and V4. And really, I can think of this as one, coefficient matrix I'll call capital A. There's this vector of C values, so I'll call that this vector C, and I'm multiplying that and setting it equal to the 0 vector. So again, we can ask ourselves, what can happen with this? Now I've written it as a homogeneous linear system. What can happen? This is just another way to interpret the question that we asked last time. One, either we have that the only solution is that the C vector is equal to the 0 vector. That is the same as this set being linearly independent. Okay, that's one option. Or, so let's write down, or our second option, like we had earlier, was that there could be infinite solutions. Last time on the other slide, I said, there's some non-zero values of C. Well, there would be infinitely many if that were the case. And this would mean the vectors would be linearly dependent. So you can see these are the same ideas that we discussed earlier, except now I'm thinking about this matrix equation, this system, this homogeneous linear system. So now that we've converted this notion of linear independence into a homogeneous linear system, I can think about what this means for using the invertible matrix theorem. What does this mean about this matrix A? Well, if the only solutions for these constants are zeros for all of them, then this matrix A would need to be invertible, because I would have a unique solution for this system, A times C equals 0. And that unique solution happens to be the trivial solution, or in other words, C equals 0. So what we can say is that in order for the vector C equals the 0 vector to be the only solution, only solution to the homogeneous system AC equals 0, we need A to be invertible. In other words, the determinant of A would not be 0. That's from the invertible matrix theorem. So we can come up with a new strategy here. Make a little divider. So our strategy, if we have n vectors, so here we have 4 vectors in R4, so we have the same number of vectors as the dimension of our space, we can decide whether or not they're linearly independent by creating this matrix where I just put the columns, I just create the columns as the vectors that I have in my set, and I check the determinant of that matrix. So our new strategy, if this is the case, first, we always want to count the number of vectors in the set we're given. That's going to give us a clue about what we can do. So if a set has a set of vectors in Rn, so maybe I'll write that out. If a set of vectors in Rn has more than n vectors, then we can automatically say that those vectors are going to be linearly dependent. One way to think about this is like if you had vectors in R2, you only need 2 vectors to span R2. So if you had 3, you would have, some redundancy there. You'd have an extra vector hanging around, and that vector would be linearly dependent. So that's one thing we can do. First, see if we have more than n vectors. Next, we can see if we have fewer than n vectors. If a set of vectors in Rn has fewer than n vectors, then we don't necessarily know right away if this is linearly independent or not, and we can't really write down a matrix here to compute the determinant because this matrix wouldn't be square. If we had fewer, oh sorry, I spelled that wrong. If we had fewer than n vectors here, we wouldn't have a square matrix. So instead, we're just going to have to, write out the whole system, just like we did in this example earlier. Write out the system of equations for the constants, just like we did in our example. For the constants, and reduce the augmented matrix. I'll just say AUG matrix because I'm running out of room. And lastly, the thing that we just showed in this example, and it turns out it's true, is that if we have exactly n vectors, so if a set of vectors in Rn has exactly n vectors, then we can create the square matrix A and compute the determinant. So if this is the case, we're just going to check the determinant of A. If the determinant is not 0, then we would have linearly independent vectors because the only solution to those constants would be zeros. If the determinant is 0, then we would have a linearly dependent set of vectors. So I hope you found this video helpful, and let me know if you have any questions.